All right, welcome back, everybody. So, the lesson number 4, we're going to describe antenna characteristics. Obviously, we know that we need an antenna to transmit the signals. There are many different types of antennas that exist and that are available, and what antenna you decide to use depends on how you want to use it, what type of signal you want to be sent, and so on. So in this lesson, we're going to kind of look at different types of antennas. We're going to take a look at radiation patterns and identify how we can read those pattern charts. We'll take a look at different types of antennas, the effective antennas on dBi and dBm, and the effective isotropic radio power. We'll take a look at different types of antennas used in our wireless networks. Understand the functions and the features of our omnidirectional antennas. The directional antennas as well. Describe various types of connectors that are actually used to connect to different antenna types. We'll take a look at the purpose and the use of various attenuators and amplifiers that are utilized in our wireless network. Look at the purpose and the features of splitters, the effects of EIRP on the antenna type, and then finally we'll evaluate and calculate the effects of antennas based on dBi, dBm, and EIRP. In addition, what we're going to do is wrap up this lesson by actually going through and taking a look at some examples and do some, we're going to do some calculations and whatnot, and take a look at some of how those calculations affect or are utilized. Okay? So there are many different types of antennas, obviously lots of different manufacturers and different vendors of antennas, but the most important thing when you're looking at an antenna is how does it radiate a wave, right? How does the signal emanate from the actual antenna? This factor has a big impact on the strength and the range of the signal, and also has an impact on legal implications because radiation beyond certain strength limits is not permitted in certain jurisdictions. We know from our previous discussions that an antenna is just basically a piece of equipment that can receive alternating current signal by letting it flow, by letting a flow of electrons move back and forth. We can then transform that energy into an electromagnetic field. Depending on the material that's actually used to construct the antenna, the thickness, the length, the physical characteristics of the antenna, the shape, it's going to generate a field in different types. And we can really define based on the physical design what that's going to look like. So you may decide that you want to take an antenna and put it into the center of an office, so you want to have to cover a conference room, so you may want to have an omnidirectional antenna. Maybe you want to put it at the end of a manufacturing aisle, or a long corridor, so you may want to have what we call a patch antenna because you want the beam focused down the hall over a long distance. The shapes of these antennas are very basic. It's the actual internal components of the antenna that causes essentially these zones that radiate more in one location or out in one direction of the antenna than in other directions on the antenna. So the first task when you're actually trying to decide what type of antenna to use is to decide what type of radiation pattern you want that antenna to have. So when you go out to Cisco.com, for example, and search on wireless antennas, you can see there's a guide, a PDF document that describes all the different antennas and their planes of radiation, or the patterns of radiation. There are essentially two planes of existence when it comes into defining the pattern of radiation from an antenna. You kind of have to look at this conceptually from a 3D experience, but we have the horizontal plane and the elevation plane. And on the diagram here you can see the top view of the H plane versus the side view, and we can see the side view of the E plane, the elevation plane. Kind of makes sense if you kind of picture this. It's almost like a donut shape in this particular case, where the pattern is radiating around the antenna in all directions. The H-plane is called the azimuth chart. It represents the radiation pattern if you're as if you're looking from the top of the antenna. And this chart shows how the signal spreads ahead, behind, to the right, to the left, but not how the signal spreads up or down, and it provides this flat or horizontal view of the plane. So the H-plane is horizontally. You know, if you have a piece of paper laying flat on a table, a piece of paper would represent that plane. The E-plane, or the elevation chart, represents the radiation pattern if you look from the side of the antenna. So it's going to show us how the signal spreads ahead, behind, on the top, and on the bottom, but now not how it spreads out from the left or the right. And we can also see the top-down view of the signal shape. Together, you can kind of extrapolate what this 3D pattern is going to look like. And we'll take a look at some of the radiation pattern charts for each of the different types of antennas a little bit later on. A way to determine the radiation pattern is to install the antenna, move around the antenna with a laptop or a signal scanner or a spectrum analyzer, and see where the strongest RSSI is, and you can kind of depict or identify what that pattern looks like. It's not really necessary because all the patterns are essentially defined, but that's one way to do that. All right, so let's take a look at the radiation pattern chart as it's applied, right? The H-plane existence and the E-plane existence. In all cases, the antenna is supposed to be in the center of this particular diagram, right? So it doesn't really it's not drawn on the diagram, but you can kind of assume that it's part of that particular view. So you can see the horizontal plane. This is an omnidirectional antenna, so it kind of makes sense that the horizontal plane is just going to be a circle because we're looking at it from the top down. We're not looking at the elevation of this particular radiation pattern. We're looking like you're laying a sheet of paper on the top of a table and you're looking down on that sheet of paper, right? You don't see how thick that paper is. If you were to stack 20 or 30 sheets of paper on top of each other, if you're looking directly down on that stack of papers, you wouldn't be able to identify how thick those papers were, or that there was even multiple pieces of paper, assuming there's no shadows and you're looking directly on the top. That's what the H-plane represents. The E-plane represents the thickness of that paper. So you have a stack of 40 or 50 sheets of paper, you're looking at it directly from the side. You can't see the horizontal pattern. You don't know how wide or how long that piece of paper is, but you know how thick the stack of paper is. So that's kind of a way of representing these different planes. Okay. The strength of a radiation pattern is going to be expressed in decibels, but the charts don't actually show distance that's reached in a certain direction. Because remember, the distance is not relevant to the actual antenna. Distance is based on how much power you're putting into the antenna, the loss of the cable, and so on. So we're not really representing any kind of power levels or distance that an antenna will be able to transmit. Because as you increase the power of the access point, obviously the distance or the transmission is going to go out further distance, right? So vendors take a reference point, which is usually chosen in the main beam of the field in front of the antenna, in the direction in which the signal is the strongest. That reference point is labeled as 0 dB. Okay? And all the other weaker points are drawn in relation to that particular reference point. Kind of see the concentric circles that are going around this pattern here. So the other points are labeled minus n dB. Depending on how much weaker the signal is, will be given will be in that given area than at the strongest point. All right. Some vendors use double representation, etc., etc. The diagram here shows an omnidirectional antenna. Each circle represents 5 dB, and the degree markings measure beam width. So beam width meaning, what is the focus of the angle, and of course omnidirectional is 360 degrees. So we see that referenced here in the horizontal plane. All right. The H-plane, like I said, shows a 360 degree pattern. A 3 dB beam width, the 3 dB beam width that you see here, or half power beam width of an antenna is for each of the polar planes. So if you look at the diagram on the right, you can kind of see this in more of a representation. Kind of the sweet spot of the elevation plane in this case is that 3 dB beam width. That's the angle between the points in the main lobe that are down from the maximum gain by 3 dB. So the E-plane on the right shows the lobes for each side. Each lobe has approximately 3 dB beam width of 120 degrees. If that makes sense. I believe it makes sense if you look at it. Okay? Now, we're not just transmitting out in both directions, right? We're not transmitting to the left and to the right. That's actually a donut-shaped pattern. So you have to kind of look at the horizontal view or the azimuth plane, azimuth view, and apply that to the elevation view, and you'll see that. Okay? Hopefully that makes sense. All right. When we look at all the other antennas in this case, you'll be able to see all the varying patterns that will exist in this particular case. In this particular slide, we're taking a look at polarization because we're generating electromagnetic waves or electromagnetic fields out of the antenna, but they're not always polarized in the same format, right? We're generating a sine wave either horizontally in a horizontal polarized loop or vertically in a vertical polarized loop. Or we can use circular polarization where we rotate the field and use both the horizontal and the vertical fields. The H and the E plane patterns are usually different. So what does that mean? That means that the antenna does not radiate in the same way in all dimensions. And that makes sense, right? You have a patch antenna, it's going to send very little over the elevation plane, but a lot in one direction on the horizontal plane. Or you have an omnidirectional antenna, which sends kind of a signal out in 360 degrees, but very little signal above and below the antenna in the elevation plane, but propagating outwards on the horizontal plane. Different antennas get applied to different applications, right? There are different reasons for using a different type of antenna based on whatever kind of coverage you need and how you want that electromagnetic field to be propagated. The antenna is going to radiate an electromagnetic field depending on what type of antenna you have implemented on that particular device. And we don't really see this reference too much when we're actually looking at wireless antenna design, or we're actually trying to select an antenna. We don't pick the polarization necessarily, but it is important to note that there is a difference between different types of antennas. The antenna is going to radiate this electromagnetic field, meaning that electric and magnetic fields are being generated, and these fields are being interpreted as data in the form of ones and zeros. Both fields are the actual wave, but the electric field is what usually represents the radiation pattern. So an electric field is defined as a variation in the electric characteristics of the space that surrounds an electric charge. It's kind of beyond the scope of this class, talking about these electromagnetic fields. We don't really get into it too much. Like it says here on the book, on the slide, Wi-Fi typically uses a vertical polarization. In a vertical polarization, we use a linear polarization, so the wave goes up and down. Horizontal polarization, the wave goes left and right. Circular polarization, the wave circles as it moves forward. If you do have multiple types of antennas, or you're trying to communicate from one vendor to another using different types of antennas, it's very important to identify what that polarization is. The antenna is actually physically what determines the polarization. You cannot identify what polarization is based on the axis point. The axis point does not determine polarization. All right. Let me see if I can kind of describe this a little bit more so that it's maybe a little easier to understand. All right. An electromagnetic wave, in this particular case, radio frequency waves, consist of coupling oscillating electric fields and magnetic fields. And these fields are always perpendicular by convention. The polarization of the electromagnetic wave is going to refer to the direction of that electric field. That's what I was just describing in the book there. Like I said, in linear polarization, the field oscillates in a single direction. In circular or elliptical polarization, the field's going to rotate at a constant rate in a plane as the wave travels. The rotation has two possible directions, right-hand sense or the left-hand sense. And again, not something we typically have to concern ourselves with in wireless, because we typically use just vertical polarization. A vertically polarized electromagnetic wave is, well, depicted here, right? The second diagram that you see, and a horizontally polarized radio frequency wave is depicted here on the top diagram. Perpendicular to the electric field is the magnetic field. So the electric field is represented here in red. The green represents the magnetic field, which is the actual radiation that gets generated at the same time that the electromagnetic field is or the electric field is being generated. Is it important to understand? Not really. I mean, in Wi-Fi, typically we're vertically polarized. There's actually a reason for that, a historical reason. In the 1950s, the very first TV signals were sent out of New York City with a much longer wavelength than Wi-Fi signals. And experimentation showed that horizontal polarization is more effective for going around the interferences that the skyscrapers caused and so on. So the radio frequency engineers decided to use vertical polarization so that we would have less interference with the TV signals and so on. Is it really important to understand? Not really. I mean, they discuss it very briefly here. Obviously, when it comes to this type of theory, you can get into a lot of math, talking about transverse electromagnetic waves and looking at coordinate frames and Jones vectors and polarization ellipses and all that stuff that I learned when I was in school, but I couldn't identify any of that stuff today. I mean, I think I remember things like Stokes parameters and coherency matrices, and I don't know. There's a whole bunch of math involved in deciding the polarization and wave propagation. But way beyond the scope of this class. All right. Now, one thing that is not beyond the scope of this class is understanding the concept of diversity. Diversity is a really important concept when it comes to dealing with multipath distortion. It is actually quite a concept that's kind of misconceived quite a bit in wireless, because it's a when people look at access points with multiple antennas, they typically don't think of diversity. They're thinking of the concept of diversity and or the concept of additional throughput or additional bandwidth or whatever it might be. But diversity is a method in telecommunications, particularly in wireless, that improves the reliability of message signaling by using different channels with different characteristics. It's used in obviously in wireless, but it's also used in other radio communication techniques, and it's used to combat things like fading, channel fading, co-channel interference, and so on. Diversity techniques also help with multipath propagation. Now, if you remember when we talked about multipath, it's a propagation phenomenon that results in the radio signals reaching the received antenna by two or more paths. You have atmospheric ducting, reflection, refraction on water bodies and surfaces and whatnot that would cause this. Multipath causes this thing called multipath interference. And it could be constructive interference, like we talked about, where we're combining signals that are in phase, or it can be destructive interference, where signals are shifted and they negate each other, which causes fading, right? So the whole concept of diversity is to deal with that, allows us to deal with that, that particular issue. Now, there are many different types of diversity schemes that exist, and we can talk about a few of those, but we'll primarily focus just on the general concepts. Okay, we typically see space diversity in the case of wireless. Space diversity means that the signal's transmitted over several different propagation paths, and then we have multiple receivers that are spaced apart that receive those paths separately, and that's why the antennas are actually a specific distance apart. We'll talk about that in a little bit here. All right. It's kind of interesting when you think about it, because I've seen people, they have these two antennas or three antennas or whatever on the AP. They'll angle them a different way because they think that both antennas are transmitting and receiving. So they're, hey, we'll get better coverage if I kind of angle this antenna this way and I angle this antenna this way. Actually, that decreases the efficiency of the wireless access point, because it reduces the ability to deal with that multipath distortion. All right. Multipath propagation is, like I said, a problem that occurs on indoor wireless networks. And one way to solve the problem is to move the client away from the zone where reflection or refraction affects the signal. The problem of where to locate the AP is usually solved by permanently mounting it in a particular location, meaning that you always have predictable outcomes. You always understand what kind of service is being provided by that access point. In the case of diversity, though, what we use is we use two antennas. We place them one wavelength away from each other, and that's where that distance comes into play. So when a client sends a frame, it contains a preamble, just like an Ethernet frame. That preamble, if you recall, in Ethernet just identifies that a frame is being sent and received, so that the client can then start to process that information. So when we're receiving the frame, the AP then alternates between both antennas to determine which one has a better signal. All right. The AP can alternate in this way because the preamble doesn't actually contain any actual data. So this happens very, very quickly, but it allows us to quickly identify which signal is better. The AP then receives the rest of the frame from the antenna that gives you the best result and uses that same antenna to send the response. Now, assuming that the client's not mobile, assuming that the AP is fixed, then you hope that that response is essentially going to follow the same path and will get the same result on the way back. All right. Older APs that use diversity have a single radio that has two antennas connected to it, and then an internal switch allows the AP to use one antenna or the other, but the AP that never uses both antennas at the same time. All right. That's why I always thought it was interesting when people were taking these antennas and they were, I mean, I've even seen scenarios where somebody removed the antennas, put a cable, and then moved the antennas to different parts of the room, thinking that one AP could then act as essentially two APs, which was completely counterproductive, obviously. Nowadays, though, both antennas can actually be used. Some of the newer APs that run, say, 802.11n or AC, they might have two antennas or six antennas or eight antennas or whatever, but they connect to different radios. We have a concept in here called MIMO, multiple input and multiple output. So these APs have the ability to receive simultaneous signals through different antennas and radios, increasing the quality of the signal. They can then combine those signals to get better signal strength, or they can do beam forming, or all kinds of interesting concepts that we'll talk about a little bit later on. Very important concept to understand about diversity is that the algorithm that the AP uses compares the signals that the AP hears from both antennas. That means that the client signal must be heard on both antennas in order for diversity to work. We need to make sure that both antennas are oriented correctly and they're placed in the right position. So in order to ensure that diversity works, the antennas need to be only in one area, not two areas. The client if you move the antennas too far away apart from each other, the signal might not even be received on one antenna. The antennas that are attached to AP should be the same. If you use a low gain antenna and a high gain antenna, obviously the antenna with high gain capability is always going to win out. And also, additionally, the coverage patterns might be different. So you can't use a patch antenna, for example, in an omnidirectional. I've seen that before, actually. I've seen where somebody actually took an AP. I've seen all kinds of crazy things, but that had two antenna ports, for diversity, of course. They left the rubber ducky antenna on one port, and then they took a patch antenna and connected it to the other port. They drilled a hole through the wall and stuck the patch antenna on the other side of the wall. And then they're thinking that antenna could then service that area separately. Some weird things I've seen. Obviously, that's not going to work. Okay? All right. There are two main families of antennas, omnidirectional and directional. Quite simply, omnidirectional antennas send the signal of the same strength in all directions. It's not obviously 100% omnidirectional, but it will send the signal in all directions. Directional antennas radiate energy in a particular direction. There's multiple types of directional antennas, but the idea is that we're focusing the beam to a specific direction, which doesn't increase the power necessarily. We can't, remember, an antenna is a passive device, so it doesn't actually amplify the signal, but it does increase the fidelity of the signal by focusing that in a specific direction. Another way of representing a change in radiation pattern is to look at angles. Okay? An omnidirectional antenna radiates all around in 360 degrees in kind of a donut shape, if you can imagine that. Whereas a directional antenna radiates towards a certain direction, but the beam might be wide or it might be narrow. Like, for example, a Yagi antenna, which is the one you see here in the middle, is a directional antenna. It has a very narrow beam width of 28 degrees up to 80 degrees, whereas a patch antenna might have a beam width of up to 36 to 55 degrees, but only in one direction. The angle for each antenna type is fixed based on the physical antenna. You can increase the distance by increasing the power into the antenna, but you cannot change the radiation pattern of the antenna. That angle that I just represented, the 28 degrees and 80 degrees and 36 and 55 degrees, that's called the beam width. The beam width is actually correlated directly to the strength of the signal in the main beam. The main beam is kind of the best possible pattern, or the best possible beam. All right. The narrower the beam, the higher the signal strength of the beam, the higher the gain. Some antennas are said to be high gain because they concentrate the beam, which allows that beam then to go very, very large distances or very long distances. All right. Again, we're not increasing the power, the effective output power of the access point. If I'm putting in 100 milliwatts of power, I'm getting out 100 milliwatts of power. It just depends on where that power is focused and what direction it's sent in. I think I used the flashlight analogy a little bit earlier. All right. Wi-Fi antennas radiate their electric and magnetic fields into the air, but could also work in the vacuum of space. Obviously, we're just sending radio frequency signals, and we do that all the time with devices that we're communicating with in space all the time. Obviously, free path loss and other types of loss may or may not exist depending on where we're sending it to. Okay. So let's take a look at some different antenna types. Then we'll take a look at some connectors, and we'll kind of wrap up this lesson here. All right. Omnidirectional antenna, pretty basic. On at least one plane, the azimuth plane, we're sending or radiating signal in all directions. We don't typically do this on the vertical plane, usually on the horizontal plane. The most basic omnidirectional antenna that you're going to see is the dual band dipole antennas. Dual band meaning 2.4 gigahertz and 5 gigahertz. It's not very powerful, but if you think about the concept, since we're sending the signal in all directions, not very powerful means, yeah, we have to radiate that power in multiple directions. So we're going to lose a lot of that gain because it's not a directional antenna, right? The antenna radiates everywhere in the horizontal plane. We can see that depicted in the red to reach clients in the whole room or on the horizontal plane, but does not radiate in all directions on the vertical plane. So meaning that depending on how the antenna is oriented, I could cover a conference room or a floor, but I couldn't cover the floor above and the floor below. That's not to say that that doesn't happen. I mean, obviously depends on where you are in that bubble. But certainly standing, if you were to place yourself directly above the antenna, you would get very low or minimal signal strength from that point. Obviously, as you move away from the antenna, the patterns are expanding like a donut in multiple directions. So you might be able to get some signal above and below the access point. So there's some examples of some different omnidirectional antennas here. I'm sure you guys have seen these many, many times. You will note that there are dots on these antennas. The dots will indicate whether it's a 5 gigahertz antenna or a 2.4 gigahertz antenna. The gold ring typically means dual band. I believe it's a blue, don't quote me on this. I haven't looked this up in a while, but I believe it's a blue dot if it's 2.4 gigahertz and it's a red dot if it's 5 gigahertz. But if it's dual band, it's going to have that gold ring around it. You can't just, I mean, they both use the RPT and these same connector types, but you can't just use a 2.4 gigahertz antenna in a 5 gigahertz scenario. All right. Yes, Mike, go ahead.
Hey Scott, what's the purpose of the swivel ability on those? For instance, we had some Cisco access points about 4 years ago that had that swivel ability. Now, if they were all swiveled in the same orientation, I could possibly see that as being advantageous. But if you just swivel them in different directions, don't you use the ability to, what was the diversity?
Yeah. So to answer your question, great question. It just has to do with having the ability to mount the AP in different positions. So if you, say, wanted to mount the AP on the ceiling, you'd want to turn the antennas down and have them oriented the same way. If you want to mount it on a wall, maybe you don't turn the antennas down, you turn the antennas vertical and so on. So on a desk or whatever it might be. Obviously, it gives you a lot more flexibility because you don't have to turn them at 90 degrees, and you can turn them in rotate them in 360 degrees. But you're right. You want to make sure that they're oriented in the same way. I mean, I've seen scenarios where the AP is not mounted exactly on a flat surface, right? It's mounted on an angled wall. So that gives you the ability to adjust those antennas so that you're knowing what the radiation pattern is of the antenna, you're able to put those antennas in their optimal position. That's essentially the purpose. But you're right, you do want to make sure that whatever you do on one antenna, you want to do on the other. Very, very important concept, okay? Now, that being said, we see it all the time, right? Somebody says, well, I'm going to turn this antenna a little bit this way, and I'm going to turn this antenna a little bit this way, because maybe that'll help me get better coverage. And actually, you're right, that will affect the diversity operation of that particular access point. So you don't want to do that. Hopefully did that answer your question, Mike?
Yep, it did.
Okay, great. Now, you do have access points that have antennas integrated, and obviously in this particular case, you have to be very careful about how you mount these access points. And if you look at the radiation patterns for these access points, you can see that essentially in the elevation plane, most of the signal, it's almost like it's a patch antenna because these are supposed to be ceiling mounted APs, right? So people still will install these vertically on a wall. Generally, depending on how close you are to the access point, it won't really have any effect on your communication. But I mean, I have these in my house, and I don't have them mounted on the ceiling. I have them mounted on the wall, but it's a small enough space that I don't really notice the difference. Just something to keep in mind. These 3700 series APs require or typically are mounted on the ceiling, and you can't really change the orientation of the antennas internally. Now, you can also implement or install high gain omnidirectional antennas. Typically, a high gain antenna would be typically something like 5.2 dBi. Now, the goal here being that you want to cover more space or more area. Again, you're not really going to increase the overall power. It's just that the points around the circle, there are more points around the circle than if you had a lower gain antenna. Obviously, a 5.2 dBi gain antenna is more than twice as high as a 2.14 dBi dipole antenna, so it's twice as powerful. But this gain is still passive. Remember, antennas do not contain an active amplifier, so we're not increasing the power output of our device. The gain is going to be achieved by reducing the E-plane angle to make it flatter. So instead of having that big donut shape, right, where you have kind of this donut shape all the way around, we have more of I don't even know what that looks like, but it's not a omnidirectional donut shape. So we're not changing the number of points on the line, we're changing the line. If you think about this for a second. So let's say in this case here, in my omnidirectional antenna, I have 20 or 30 points on this line here. All right, well, when I go down to this I still have 20 or 30 points, but they're going to be further apart. Does that make sense? So we're not increasing the power, we're distributing the power in a different way. Okay. It doesn't provide, this particular antenna doesn't really provide a whole lot of coverage above or below it, but it does go through walls and through construction material very well. So you may run into a situation where you have to install one of those antennas. This is what that high gain antenna might look like. And remember, this book was published in 2015, so I always tell people when we're talking about specific technology, always reference Cisco's documentation to get the latest information, because it does get updated. All right. All right. So when you look at these antennas placed together, we have an even higher gain antenna, 12 dBi mask mount omnidirectional antenna. And you can see now, instead of that donut shape or whatever this shape is above, we have an even more compressed elevation plane. This would be a mast mount antenna. If you have an antenna that's going to be mounted on a mast instead of a ceiling, obviously this is more for an outdoor application. The gain can be increased to cover a larger area, but the increased coverage comes at a cost in the thickness of the donut, I guess you could say. So coverage up and down is poorer with a 12 dBi antenna, but you get a much larger range. Again, keep in mind these patterns, these radiation pattern diagrams do not describe the distance, because the distance is relative to the input power, but it describes the pattern itself. All right. All right. Now, a directional antenna is designed to cover one specific direction. In an indoor environment, the antennas are typically placed on a wall. They're called patch antennas, and they provide either coverage in a big meeting space, or down a hallway or a corridor, or down an aisle in a warehouse or something like that. A directional antenna provides more gain than your basic omnidirectional antenna. But again, we're not changing the power. We're just directing the power into a specific tube or a funnel. So the shape of the antenna coverage pattern shows that it follows one floor coverage logic, meaning that we don't have any coverage above and below the antenna, but we don't have a very large vertical range either, or even a horizontal range behind the patch. Only in front of the patch we have a large horizontal range. Then we start to get into some of the newer technology, like a 6-element MIMO patch array antenna, which is, MIMO stands for multiple input and multiple output. We'll talk about that technology a little bit later on in detail. We're going to talk about a lot of the enhancements to wireless over the years, and MIMO is one of those technologies. But we see a patch antenna, obviously ideal for indoor, but it can be used outdoors as well. The nice thing about this particular design is it's relatively benign, right? You don't see a bunch of weird alien-looking antennas sticking out of it and so on. It radiates slightly in the back, but primarily in the front, and again, in a long distance. Let's take a look at what that radiation pattern might look like. This is a Yagi antenna, so this is going to be a much more focused beam width, and you can see both the horizontal and the H-plane and the E-plane have almost the exact same pattern, which means you're kind of like it's kind of like a tube of radiation. Right? Now we know the goal here is to transmit over a long distance. They call it a comb shape. I guess it kind of looks like a comb. But the pattern of this antenna is specific. So rather than thin on the vertical and horizontal planes, rather than omnidirectional on the horizontal plane and kind of tubular on the vertical plane, It's very thin on the horizontal and vertical plane, so it gives us a very narrow beam that allows us to radiate in large distances. It has slight radiation in the back because of the manufacturing process. Most Yagis will have a small radiation field in the back. That's called the butterfly effect. We also get these side lobes, but which means you are going to get some coverage there, but the goal here is covering long corridors or long distances. And they have indoor, outdoor, ceiling mount, mast mount variations. One issue to consider when you're installing this particular type of antenna is the polarity, right? Because with a patch, which is a rectangle, the polarity is kind of intuitive. You stick it on the wall, right? With a Yagi, which the base is kind of a square, you would have to read the vendor specifications to determine how to mount the antenna. Remember, if I turn this, and usually they'll have a designation on the antenna that'll indicate the polarity, but if you see how this one's kind of on the left is kind of mounted sideways, this one's mounted vertically, the logo might indicate that. I'm not suggesting that's the case here, but usually they'll have some sort of designation on there to identify how it's supposed to be mounted. If you actually physically mount it the wrong way, you're going to change the polarity of the signal, which means that the receiving antenna won't be able to receive the information. The next example of a directional antenna is the parabolic dish, right? Obviously called that for this reason. It looks like a parabolic dish. Typically used in a point-to-point scenario. Very similar pattern to the Yagi antenna, but much higher gain. So instead of looking at maybe 13 or 10 dBi, we're looking at maybe 21 dBi in this particular case. So that makes it almost 100 times as powerful as the patch antennas. Like the Yagi antenna, the parabolic dish antenna has a visible butterfly effect. So you've got the side lobes and the output from the back. That's part of the manufacturing process. Testing the antenna link from the ground next to the antenna is useful. Polarization might be considered here, but usually with these parabolic dishes, there's a mounting point, and it's pretty obvious how the dish is supposed to be mounted. Also, the logo will usually indicate that. Now, depending on the manufacturer, depending on the actual access point and the physical equipment, you'll have different types of connectors. Cisco typically uses an RPTNC connector, and other vendors have other types of connectors. I'm sure you guys have seen the SMA connectors before, or RPSMA, MC connectors, MMCX connectors, and so on. But Cisco will typically use the RPTNC connectors. Connecting antennas to the AP, very simple, just twist it on, right? Now what's interesting is that this is actually kind of a regulated industry. If an antenna is not supposed to be directly connected to the AP, it'll have a different connector type. And if the antenna from one manufacturer has a specific amount of gain, which would exceed the EIRP that you're supposed to have for that particular system, then what would happen? Well, you would run into a scenario where you would have to have a different connector for that type of antenna, so it couldn't be connected. A lot of countries have regulations that require the AP manufacturer to use a specific connector type to connect its antennas. It's certainly possible to buy the cabling and the connectors and circumvent those regulations or even follow those regulations, but from a manufacturing perspective, it is regulated. All right. Now, if an antenna is not directly connected to the AP, you can have a cable, of course, usually coax. There is some loss introduced in that connection, and we measure that loss in dBs, and that goes into calculating the overall effective isotropic radio power. All right. We'll take a look at some of those examples here in a little bit. In addition to the cabling and the connectors and the antennas and the actual source of the information, you can also have, you can add attenuators and amplifiers. Quite simply, an attenuator is anything that reduces the amplitude of the signal. It doesn't change the frequency, it doesn't change the wavelength, it just decreases the amplitude. Or amplifiers, of course, will increase the amplitude of the signal. Typically, we'll see these in licensed bands, not unlicensed bands. But you know, obviously, the goal here is to provide some sort of active amplification, not passive amplification. So we're not changing the focus of the beam. That's the role of the antenna. But our goal is to increase the overall strength. So we're actually going to apply some sort of active process that amplifies the signal. Make sure that when you're deploying wireless networks that you comply with the maximum EIRP that's allowed in your area, governed by whatever governing body is applied in that particular area. All right. If it turns out that you have, for some reason, I don't know why this would happen, but you have a signal that is too strong and you want to make sure that you're meeting the regulations and requirements, you can install an attenuator to reduce the transmitter signal. Now, attenuators typically don't always have to be active. They're filters, so they can be passive. In other words, they don't have to necessarily have an external power source connected to them. But if the signal that's sent from the antenna is too strong for that location, and we need to bleed some of that signal off, we can use an attenuator to do that. Okay. If you're dealing with outdoor wireless, oftentimes you'll want to install something called a lightning arrestor. I want to be very clear about this because I've run into a situation with a client where this occurred. We had a lightning arrestor installed, which gets installed between the antenna and the cable and subsequently gets grounded to a ground. And lightning struck the antenna and the equipment was destroyed. Lightning arrestors are not designed to protect against direct lightning strikes. If you want to protect against direct lightning strikes, your equipment, you need to essentially, I wouldn't say air gap, but don't have twisted pair Ethernet going from your wireless bridge into your infrastructure. Put in some media converter with fiber optic cabling to create that non-conductive gap. Lightning arrestors are designed to provide protection from electrostatic energy in the area, right? So if lightning strikes nearby, or if you have a highly charged environment and you get a static discharge, the lightning arrestor would protect that, if that makes sense. Okay. But a direct lightning strike, most likely not going to be protected in this case. All right. All right. Oh, as I was mentioning before, if you want to protect your infrastructure equipment, make sure that you put into place a fiber optic disconnect, right? So you've got your bridge, outdoor antenna, you put in some sort of fiber optic transceiver or media converter, run at least 1 meter of fiber optic cable so that in the event that there's a direct lightning strike, you're not going to lose your switch or your infrastructure stuff. Okay. Now there's many other things that you can do with wireless. You can add splitters. Sometimes it's used if you want to have multiple types of antennas. You're trying to cover a large outdoor area, but they have the coverage has different requirements. So you might want a Yagi antenna in one place, or a patch antenna in one place, and you want a parabolic dish in another place. A splitter essentially allows the signal that comes from the cable to be split into two so that the signal can be sent over two different antennas. Important downside is the loss of power on the cable. You're going to typically see about a 4 dB loss to the system with a splitter, and that's going to be seen in both antennas. So each antenna is going to suffer a 4 dB loss. So at 2.4 gigahertz, this loss reduces the gain of the dish from 21 dBi to 17 dBi. It provides a distance advantage, but not twice the amount. Remember, we're losing, just because we're going down by 4 doesn't mean we're only losing a minimal amount of power. We're losing more than twice the power. All right. So when you reduce the gain on one antenna to 17 dBi, the distance drops from 20 miles to about 13 miles. It's a pretty significant difference. The second drawback is that the throughput is reduced by about 50% because the repeater must receive, buffer, and transmit data on the same channel. Using a splitter, not usually recommended, primarily for that reason. All right. Remember, we're not creating additional signals. We're just taking the same signal and duplicating it. The last concept we've already kind of talked about, EIRP. And this is something that you guys will have to calculate on the exam as well. But keep in mind, from a production standpoint and from an operational standpoint, the total EIRP, or the transmit power, is governed by whatever governing body exists in your particular region. In the United States, it's the FCC. The FCC determined that 36 dBm, or 4 watts, is the maximum transmit power. Now again, that's not necessarily applicable in an unlicensed band. That's in licensed bands as well. But it is important to know the effect of the antenna on your total EIRP, or transmit power. So you have to pick the appropriate antenna and the transmit power settings based on the regulations for the country or the region that you're in. All right, so look at this example. The transmit power is expressed in milliwatts. So if we do the math, we will have to convert the milliwatts to dBm. So in this particular case, 17 dBm is actually equal to 50 milliwatts. All right. By the way, how did we do that? Any ideas? 17 dBm to 15 milliwatt, or 50 milliwatts. Well, we can't get 17 if we do our 10 plus 10 plus whatever. We can't get 17, so we have to do 10 plus 10 plus 10, or excuse me, 10 plus 10, which gives us our, well, to get to our 50. Well, I'll tell you what, we'll look at some examples. We have some examples that we'll take a look at in that we won't do it tonight. We'll start off with that first thing in the morning. I had some examples I wanted to go through and doing these calculations, but I think it's better than just kind of explaining this one, that we actually take a look at some real world examples, and I'll go through those when we're fresh in the morning, okay? All right. Let's see. Yeah, I think I'll do that discovery in the morning. I'll just do that as a separate video. So that concludes this chapter. I haven't done the summary yet because we haven't done the discovery yet, but I'm going to go ahead and we'll pause here for today. In the next video, we'll go ahead and do some examples of calculations, calculating EIRP and choosing the right antenna. It's a very important concept. And then tomorrow we'll just continue on. We're going to be getting into some lab exercises tomorrow. Actually, quite a bit to cover tomorrow. So we'll start right at 9 o'clock Central Time. If you guys have any questions, feel free to email me. Tiju, I'll provide you my information tomorrow in the chat window. So if you have any questions, you can contact me. Okay? So that concludes day number 1.